cs407 Numerical Analysis, Section 4.3 Estimating Derivatives and Richardson Extrapolation. So, determining the derivative of function f at a given point is not trivial in the numerical sense, even though the analytic version of the problem is often pretty easy. As a child of about 4 or 5, I used to accompany my father to the university, and the math professors taught me that the derivative of x squared is 2x, and they would tell me to go around and say that to people, and it would produce shocked looks on their face, even though it was a fairly trivial problem that a child could memorize. It would get laughs and chuckles from the math faculty and students. If f can be computed with n digits of precision, it's often difficult to calculate f prime with n digits of precision from a numerical standpoint. The difficulty can be traced to the subtraction between quantities that are nearly equal, which we found in the past has given us trouble with errors. In this chapter, we'll look at several alternatives for numerical calculations of first and second order derivatives. Let's begin with the obvious method. So, the obvious method for calculating the derivative is based on the definition of the derivative. F prime of x is approximately equal to 1 over h times f of x plus h minus f of x for one or more very small values of h, and that will give us the derivative. And the error involved in this is going to be minus 1/2 h second derivative of f at xi, which is about O of h, and xi is an interval having endpoints x and x plus h. We get this error term using the Taylor series for f of x plus h, giving us another use of Taylor series. I did promise you they would be important in this course. This error is always present even if we have infinite precision. We can expect worse errors when the calculations are performed on a computer with finite word length. Let's take a look at an example. So, in section 1.1, the program named first that we created used the one-sided rule to approximate the first derivative of the function f of x is equal to sine of x at x equals 0.5. What happens when we do a large number of iterations? I think we had done 10 originally. What happens when we do 50? Well, what ends up happening is you can see that the error here grows to almost all the you have a complete loss of precision after 50 points, actually after about 27 points. We lose all the significant digits. When we examine the output, we find that a good approximation of 0.87758 was found, but this number deteriorated as the process continued all the way down to 0. Basically, this was caused by subtraction of two nearly equal quantities, f of x plus h minus f of x, resulting in loss of significant digits, as well as a magnification of the effect by dividing by a small value of h. In other words, we need to stop the iteration sooner. Well, when to stop? Well, last slide we needed to stop things sooner. Common question is, when do you actually stop? In this case, what we could do is we can monitor the iterations to determine when they settle down, namely when two successive ones are within a prescribed tolerance of one another or an error term. We can also give a truncation error term to determine when to stop. If we want 6 significant digits of accuracy in the results, we can set the error term, which we derived again from the Taylor series, less than 1/2 times 10 to the 6th, and we would find that n is about 9.97, or needs to be greater than 9.97, so we should stop after about 10 steps in the process. And again, that's another use of Taylor series for numerical analysis and calculations. So, we'd like to see if we can actually find an even better way to approximate f prime of x. In particular, one in which the error behaves like O of h squared. One method is easily obtained by using the following two Taylor series for f of x plus h and f of x minus h. We subtract these two, and we get f of x plus h minus f of x minus h is equal to 2h f prime of x plus 2/3 h cubed f triple prime of x plus 2 over 5 h to the fifth derivative of f evaluated x, which gives us a way of expressing f prime of x by doing some simple algebra. We saw this type of method in we saw this type of trick in Newton's method, and in the Rongberg method of integration we'll see it again in section 5.2. It's advantageous to have the convergence of a numerical process occur with higher powers, some quantity when approaching zero. This leads us to the f prime of x central difference rule. Basically, we can also express the result from the previous slide in the following way. F prime of x is equal to 1 over 2h times f of x plus h minus f of x minus h. This is called the central difference rule. With an error whose leading term is 1 minus 1 over 6 h squared f triple prime of x, which makes it O of h squared. This is the error term for the central difference rule. Note that we're assuming the third derivative is continuous over the interval from x minus h to x plus h. When you modify the program first so that it uses the central difference formula to approximate the first derivative of sine of x at x equals 0.5, you get a good approximation a lot quicker. So here's where we did that. We modified the program first so that it uses the central difference formula to approximate the first derivative of sine of x at 0.5. Top program uses the central difference rule. This one here uses the central difference rule, while the bottom uses the original formula. It's clear to see when looking at the error. You can see the errors up here converge much faster. Note the smallest error was obtained around step 9 here. We're still going to encounter the same problem that we got in example 1 if you run it all the way out to 50 or 100 iterations. So it's good to put a check in as to when to cut off the iterations for some error value at some point in the code. Now let's turn our attention to a process called Richardson Extrapolation. So consider again f prime of x is equal to 1 over 2h f of x plus h minus f of x minus h squared over 3 factorial f triple prime of x minus h to the 4th over 5, fifth derivative of f evaluated at x. We can write this in a simpler form. F prime of x is 1 over 2h f of x plus h minus f of x minus h plus a2 h squared plus a4 h to the 4th plus a6 h to the 6th, where a2, a4, a6, etc. are values that depend on f and x. When we have such information available about a numeric process, it's possible to use a powerful technique known as Richardson Extrapolation to wring more accuracy out of the method. This procedure is now going to be explained using the second equation as our model. The second equation here is labeled as 6 on page 190 of the text. So for Richardson Extrapolation, we hold f and x fixed, and we define a function of h by the formula var phi of h is equal to 1 over 2h times f of x plus h minus f of x minus h, where var phi of h is an approximation of f prime of x with error O of h squared. We want to compute the limit as h goes to 0 of var phi of h in order to get f prime of x. Richardson Extrapolation seeks to estimate the limiting value at 0 for some computed value phi of h near 0. Obviously, we can take any convenient sequence h sub n that converges to 0, calculate var phi of h sub n from the first equation, and then we can use these as approximations to f prime of x. But there's something actually more clever that can be done. So suppose we compute var phi of h for some h and then compute var phi of h over 2. Then we get the following formulae for var phi of h and var phi of h over 2. And, well, maybe they're not so simple. Anyway, we can multiply the second equation by 4 and subtract it from the first equation, and then divide by minus 3 and rearrange to get the series at the bottom here, which is pretty cool. Basically, by adding 1/3 of var phi of h over 2 minus var phi of h to var phi of h over 2, we've apparently improved this to O of h4, because this error series that accompanies this new combination begins with 1/4 a4 times h to the fourth. Since h is going to be very small, this is going to be a really dramatic improvement for us. But it gets better. We can repeat this process by letting regular phi of h equal 4/3 var phi of h over 2 minus 1/3 var phi of h. And then notice that phi is different than the symbol var phi that we used in the previous slide. It's pretty darn subtle. So this phi is different than this one. But we can make this substitution, and then we get the following equations for phi of h and phi of h over 2. And again, we can do some algebra and eliminate the first term and end up with a linear combination of phi. There's actually quite a bit of algebra and trickery, but again we have an improvement to precision O of h to the sixth, as you can see here in this term. Now to top it off, note that the same procedure can be repeated over and over again to kill higher and higher terms in the error. This is called Richardson Extrapolation. Essentially the same situation will arise in Chapter 5, where we'll look at Romberg's algorithm for numerical integration. Therefore, it's desirable to have a general discussion of the procedure here. We'll start with an equation that includes both situations. So we'll let var phi be a function such that var phi of h is equal to L minus the summation k equal 1 to infinity of a sub 2k times h raised to the 2k, where the a2k coefficients are not known. This is not interpreted as the definition of var phi, but as a property that it actually possesses. We assume that var phi can be computed for any h greater than 0, and that our objective is to compute L using var phi. We can then select a convenient h and compute the numbers dn0 equal var phi of h over 2n for n greater than 0. So specifically, d of n0 is L plus the series from k equal 1 to infinity of a k0 h over 2n raised to the 2k, where a k0 is equal to the coefficient minus a sub 2k. These quantities d and 0 give us a crude estimate of the unknown number that is the result of the limit as x goes to 0 of var phi of x. More accurate estimates are obtained by the Richardson Extrapolation formula given in the bottom of this slide, and that's kind of a messy formula. But this leads us to the Richardson Extrapolation theorem. And those quantities d of nm are defined in the Richardson Extrapolation process, and they obey the equation d of nm is equal to L plus the summation of the terms a km times h divided by 2n. And in the proof we actually show that d of n sub n is equal to L plus the summation of these two terms. Now, since this h over 2 to the n is very small, this indicates that dnm will approach L very rapidly. And in fact, it will approach it on this order, which is absolutely astounding. So in practice, what we can do is we can arrange the quantities as a two-dimensional triangular array as follows. And we can calculate those beginning at d00. This thankfully leads us to an algorithm for Richardson Extrapolation, and we'll use the algorithm in related pseudocode and lab exercises. But thankfully, we won't have to do any of these by hand. So, the algorithm for Richardson Extrapolation is we write a function for var phi. And then we decide on suitable values of capital N and H. And for I goes from 0 to n, we compute d of I comma 0 is equal to var phi of h divided by 2i. And then we compute the dij's. And again, this one is going to use the formula that we derived about 3 slides back for d of n comma n. And there is a slight rearrangement here that improves its numerical properties. Now that we have an algorithm, we can go about converting it into appropriate pseudocode. So the input to this procedure will be a function f. A specific point x a value of h and a number n signifying how many rows in the array are to be computed. The output will be the array we talked about in the previous slide. We can then test the derivative procedure using a program called test derivative. Here we're going to let f of x equal sine of x, and x0 is 1.23095941154, and then we're going to call the derivative procedure. Now here f prime of x is going to be cosine of x, and when we evaluate cosine of x at that value, we're going to get about a third. When this gets coded up on the computer, the authors reported that the most accurate value occurs at D41, which is 0.333334333, which is pretty good. There's also mathematical software with algebraic manipulation capabilities, and using that we can write a computer program to find derivatives symbolically for a rather large class of functions, such as the ones you encountered in calculus. Now let's look at another strategy for approximating first derivative formulas, namely our friend polynomial interpolation. Note that finally note in this procedure that you would actually have to code the function f of x or pass it as a function point. But let's turn our attention to interpolation. So this is an important general strategy that can be used to approximate derivatives as well as integrals and other quantities. So the function f is first approximated by a polynomial p, so that f of x is approximately equal to p of x. We then proceed to an approximation of f prime of x is approximately p prime of x. Of course, this strategy should be used very cautiously because the behavior of interpolating polynomials can be oscillatory, as you've seen in some of the labs. In practice, the approximating polynomial p is often determined by interpolation at a few points. For example, suppose that p is a polynomial of degree at most 1 that interpolates f at two nodes, x0 and x1. So f prime of x is approximately equal to p1 of x prime, which is equal to the divided difference f of x0 x1, which you know from section 4.1 is f of x1 minus f of x0 divided by x1 minus x0. And hopefully you've gotten very good at doing those divided differences. The forward and central difference is basically if we have f of x0 equals x and x1 is equal to x plus h, then the formula is the one previously considered, which is f prime of x is equal to 1 over h f of x plus h minus f of h. And you've seen that formula several times throughout calculus, and that's the forward difference with two nodes. Now, if x0 is equal to x minus h and x1 is x plus h, the resulting formula is f prime of x is equal to 1 over 2h of f of x plus h minus f of x minus h, and that's the central difference with two nodes. Now let's take a look at three nodes, x0, x1, x2. Here we have the interpolating polynomial p2 of x is f of x0 plus the divided difference x0, x1 times x minus x0 plus f of the divided difference of x0, x1, x2 times x minus x0 times x minus x1, and here is its derivative. P2 prime of x is f at the divided difference x0, x1, divided difference x0, x1, x2 times 2x minus x0 minus x1. And if evaluating f prime of x when x is equal to 1/2 x0 plus x1, then the correction term actually turns out to be 0. Now here the right hand side consists of two terms. The first is a previous estimate, and the second is a refinement of the correction term. Thus the first term in this case must be more accurate than those in other cases because the correction term actually adds nothing to it. Now let's take a look at four interpolation points. So as a final example, consider four interpolation points x0, x1, x2, x3. The interpolating polynomial within is equal to 3 is given by p3 of x, which you can see here. And we can calculate its derivative. This is called the central difference with four nodes. Note that there's a special case that occurs when you select x0 is equal to x minus h, x1 is equal to x plus h, x2 is x minus 2h, and x3 is x plus 2h, as depicted in this slide, or in this rather fuzzy graphic from the text. When you have that, the error term is O of h5, which is pretty good convergence. Now let's look at how we can deal with second derivatives. Well, again, this comes back to Taylor series, and in the numerical solution of differential equations, we oftentimes have to approximate second derivatives. We'll derive the most important formula for accomplishing this. Simply, we're going to add the two Taylor series for f of x plus h and f of x minus h, which we had derived before, and basically what we come up with is f double prime of x is 1 over h squared f of x plus h minus 2 f of x plus 2, or plus f of x minus h, and that's going to give us error term O of h squared. This is called the central difference formula, and the error term for f double prime of x. So, the last example in this section uses program first in the central difference formula for f double prime of x to approximate the second derivative of the function f of x is equal to sine of x at x is equal to 0.5. And using the error term, we can see about 4 iterations are required for a good approximation, which is equal to minus 0.47942. The least error of 3.1 times 10 to the 9th was obtained at iteration 6. Approximate derivative formulas for higher orders can be obtained by using unequally spaced points, such as the Chebyshev nodes. An interesting question is how noise in the evaluation of f of x affects computations of derivatives when using the standard formula. The formulas for derivatives are derived with the expectation that the evaluation of the function at any point is possible with complete precision. That's a pretty big assumption sometimes, but usually for the functions we'll work with, they'll behave nicely, and so that's good. Then the approximate derivative produced by the formula differs from the actual derivative by a quantity called the error term. And this error term involves the spacing of the sample points and some higher order derivative of the function. If there are errors in the values of the function, otherwise known as noise, they can make the whole process ineffective. Those errors can overwhelm the error inherent in the formulas. The inherent error arises from the fact that in deriving the formula as a Taylor series, we truncate it after only a few terms. This is called the truncation error, and it's present even if the evaluation of the function at the required sample points is absolutely correct. So, next time we'll take a look at numerical integration.